In these two examples, we're actually, maybe we'll graph the function afterwards, but I'll show you how to check just by doing the limit whether the function is continuous, so you don't have to graph it. We have this nice definition, right? So if I'm asking if the function f is continuous at x equals 3, what I'm really asking is the limit as x goes to 3 of f of x equal to f of 3. So that's what I'm checking. So all I have to do is do the limit. And of course we know how to do that, right? We've been spending all week on it. Limit as x goes to 3 of this mess. Now I don't want to do anything with the 6, right? Because it's just equal to 6. That's one of those, that special point, right? So I want near 3, not at 3. I'm going to look at this part. 2x squared minus 5x minus 3 over x minus 3. And of course, if I put in 3, I'm going to end up with a 0 over 0. This is the same deal that we've been seeing. So let's see what that does for me if I try to deal with the top. Hopefully, it'll factor out. Something will look very nice here. So I'm going to factor this thing. Let's see if you want to stand over here so you can see what it is. I got 2x and x. And then I've got 3, so I've got 1 and 3, but I have a minus and a 5, so it's got to be 6 minus 6 plus 1, right? So minus 3 and then plus 1. Okay, that'll give me 5. Minus 5. So now you can see that those cancel out. And then I have just to take the limit as x goes to 3 of 2x plus 1, which is a nice easy limit. I'm just going to throw in the 3. Right, so I got 6 plus 1, and my answer is 7. So it looks like this one is not continuous because the value of f at 3 is given as 6, but the limit is 7. Okay, so if I did want to graph this, I would know that I'd have a line everywhere except at 3, and at 3 I'd have one of those removable points, like a little circle and then the dot. If you just stuck this into Desmos or into your calculator without doing this bit, then you just have the line and you wouldn't know what was going on because they won't always tell you. So you do need to actually do the limit. I spent a lot of time trying to figure out how to get your graphing software to graph that extra point, which I don't even know how to do because I never bother with that. Okay, so we're going to do a different one that's a little bit different. I guess I'll use f of x again, so I don't have to rewrite that, but this is a different function. This is the second example. This one is, well, these are all pretty much going to be piecewise defined, but this one is a little bit different because rather than being the same value everywhere except for at a point, this one is definitely like two different functions on two different parts of the domain. So if I'm looking to take the limit here, I'm going to have to look at the limit from the left-hand side and the right-hand side because the function is different on each piece of that, okay? So first of all, I have to figure out if the limit exists, and then I have to figure out if it's the right value. Okay, so let's see. Limit as x goes to 3 from the left of my function f of x. So from the left is numbers less than 3, so that would be my first one here. So that's just 3x minus 5. So I stick in a 3. 9 minus 5, that gives me 4. Okay. Now, I'm going to put it down here a little bit so we have a little space. I go from the right-hand side. From the right-hand side, it's the other formula for numbers greater than 3. is going to be x minus 1 quantity squared. So that gives me 3 minus 1 squared. So 2 squared is also 4. So the limit exists. So that's good. So the limit exists. So it's the same from both sides. And in fact, f of 3, what's f of 3? It's going to be what you get when you evaluate here. So it's clear that it's going to 4. So in this case, yes, the function is continuous. So these two formulas, these two functions, this line and this parabola, meet up at the point x equal 3. I could have put that at the end of the previous one, but whatever. They were shorter than I thought they would be.